Today I am going to talk about one of the most popular algorithms in numerical linear algebra, so-called QR algorithm. But first I would like to say a couple words about people who invented this algorithm. On the left photo you can see a mathematician from the Soviet Union, Vera Nikolaevna Kublanovskaya. She contributed a lot to computational methods for solving different problems, especially spectral problems of algebra. And she solved a lot of different problems, such as algorithm for solution of a complete eigenvalue problem, method of solving the complete eigenvalue problem for a degenerate matrix, methods and algorithms of solving spectral problems for polynomial and rational matrices. But probably she is the most famous for her QR algorithm for computing eigenvalues and eigenvectors, which she proposed in 1961, and this method has been named as one of the 10 most important algorithms of the 20th century. At the same time, this algorithm was proposed independently by the English computer scientist John Francis in 1959. And John Francis, on the right photo, he's an English computer scientist who published his work related to QR algorithm in 1961. And actually he never knew what impact his work had for the linear algebra, for numerical linear algebra. And he was actually a computer scientist, and his area of interests were artificial intelligence, computer languages, and systems engineering. And after he proposed QR algorithm, he actually left the field of numerical computation. He worked for different industrial organizations, and only in 2007 he found out what impact actually had his algorithm for the numerical linear algebra, and he was awarded a University of Sussex honorary doctorate only in July 2015. And today we are going to study this algorithm. Let's start. First, I would like to discuss the general idea of this method. First of all, QR algorithm allows us to compute all eigenvalues and eigenvectors of a particular matrix A. And for example, if you remember the deflation method, I mentioned that theoretically we also can find all eigenvalues, but nobody does that because of the growth of round of error. This method doesn't have this issue, and usually we use this method in order to compute all eigenvalues of a symmetric matrix. Nowadays there are a lot of variations of this method, but we will consider the approach. We will follow these steps. First, we consider symmetric three-diagonal matrix. What it means, you already know. Three-diagonal, we have non-zero entries in the matrix, lie either on the diagonal or on the sub-diagonals directly above or below the diagonal. If this is not the case, if we do not have this type of matrix, we have more or less arbitrary matrix, first what we should do is we should apply Householder method, what I described on previous lecture. And Householder method allows us to transform our matrix into three-diagonal matrix, similar to what I show you here. So we consider non-zero entries on the main diagonal as A1, AN, and non-zero entries for sub diagonals B2, Bn. Here I can write down Bn. So when there are different variations, what we can have? We can have, for example, B2 equals to 0, or let's say Bn equals to 0. Then this, let's say, matrix A1 or An immediately produces an eigenvalue A1 or An of matrix A. And this simplifies our calculations. And QR method takes advantage of this observation by decreasing the values of the entries below the main diagonal until B2 equals to 0 or Bn equals to 0. Why approximation sign? Because when we apply iteration, most likely we won't get exactly 0. We will get just very small numbers, and at certain level, at certain step, we can assume that these values can be considered as 0. For example, if we have Bj equals to 0 for some j between, let's say, 2 and n, the problem also can be reduced to considering, instead of matrix A, smaller matrices. And we have these matrices here. Here we have slightly reduced matrix. Here it's j minus 1, and here we start j to n. And here also Bn, but here Bj minus 1. J minus 1 and Bn entries. If none of Bj are 0, the QR method proceeds by forming a sequence of matrices A1, A2, A3 as follows. First, we define A1 as our original matrix A, and we assume that A1 can be represented as a product of two matrices where Q1 is orthogonal matrix and R1 is upper triangular matrix. Step number 2, we compute A2 as a product, reverse product of R1, Q1. Well, in general, the intuition about that is following. So, we represent matrix AI as a product of two matrices Qi and Ry, where Qi is orthogonal matrix and Ri is upper triangular matrix. When we define AI plus 1 as a product of Ri and Qi in reverse direction. But since we deal with orthogonal matrix, we can write down this expression. This equality holds by definition of orthogonal matrices. You can recall it from one of a previous lecture where I talked about orthogonal matrices. So, and we can say that if we combine these two formulas from this step, we can write down AI plus 1 as this product. We simply substitute instead of I this expression. And this is what we get. And we can use it because Qi is orthogonal matrix. So this ensures that our matrix A, I plus 1, is symmetric and tridiagonal with the same eigenvalues as our original matrix A. Actually, with the same eigenvalues as matrix AI, by induction, we can go back step by step and we can conclude that this matrix AI plus 1 will have the same eigenvalues as our original matrix A. And matrix AI plus 1 tends to a diagonal matrix. And these eigenvalues will be along the diagonal. Eigenvalues what actually we need and what we want to compute. So this is the idea of this method. In order to understand how the QR method works, first we need to understand a very important conception, so-called Givens rotations, because our method is based on a sequence of several Givens rotations. So, when we talk about rotation, there are two possible choices: rotation of the axis and a rotation of the object relative to a fixed axis. Let's consider two-dimensional case. Let's say that in two-dimensional case we have the matrix that rotates given vector v0 by counterclockwise direction in a fixed coordinate system. How we can represent that? Let's look at the left coordinate system. Let's say we have x tilde, y tilde with our axis, and let's say we have vector v0 and we want to rotate this vector in counterclockwise direction, and we have angle theta, and as a result we will get vector v prime. So in this particular case we have fixed axis and we rotate vector. For this case our rotation matrix, let's say P, or another notation you may see in the literature, R with index theta. This is the same, it's just different notation, and R stands for rotation matrix. So this matrix will look like this one. Let's say matrix 1. So our vector v prime we can compute by multiplying our rotation matrix on our original vector v0. On the other hand, consider the matrix that rotates the coordinate system. And here we have x tilde, y tilde with our axis. And let's say we have vector v0. And now instead of rotating vector v0, we rotate our coordinate system. Let's say we rotate coordinate system. As a result, we will get, let's say, x prime, y prime. This is our new coordinate system. And our rotation matrix in this case will be, let's say, a prime theta. It's the same as, again, as p prime, and this particular matrix can be obtained by rotation matrix, which is the transpose of a fixed axis matrix. We can get A prime from matrix A. Just transpose it. Let's say this is 2. So, as we can see, we looked at the two cases. On the left side, we rotated vector in counterclockwise direction, and we had fixed coordinate system. On the right side, we fixed our vector and we rotated our coordinate system. These are just two approaches, and you may see both of them in the literature. Now we are ready to formulate the definition for two-dimensional case. In two-dimensional case, consider the matrix P that rotates a given vector v0 by counterclockwise direction in a fixed coordinate system on angle theta. Then this matrix is called a rotation matrix. So P is our rotation matrix, and vector v prime equals to the product of this matrix P and original vector v0. So we claim that exists such angle theta and indexes I doesn't equal to j, such that rotation matrix can be represented as follows. These are elements of our rotation matrix for two-dimensional case. In order to apply rotation, we should just recall basic multiplication rules, how to multiply vector on matrix, and vector v in this case is just arbitrary vector with components x, y, and formula 3 represents the result of the rotation of a vector v. So we can derive similar formulas for three-dimensional case. Actually, what I provide you here, I give you three basic rotation matrices. Rotate vector by an angle theta about the x, y, and zeta axis in 3 dimensions using the right hand rule. Here I just write. Here was used right hand rule. What it is, that coordinate system rotations of the x, y, and z axis in a counterclockwise direction with theta positive. Let's solve simple example. Assume that we want to rotate toward y-axis vector v aligned with the x-axis. How it works? We have vector v with components 1, 0, 0, and we have angle theta equals to 90 degrees. How it should look like? We have vector v here. Let's say this is 1, this is 0. We have angle theta and we want to rotate our vector, and theta equals to 90 degrees. And as a result, we want to get vector, let's say v prime, and here how it works. We will use right hand rule, and we will pick rotation matrix AZ. We know angle theta, we want 90 degrees. We should simply multiply our rotation matrix on our original vector v, and as a result we will get this vector. Let's say this is our v prime vector. And as we can see, 0, 1, 0, it exactly tells us that this vector belongs to y-axis. This is exactly what we wanted. Now let's consider another example. Find a rotation matrix P with the property that the product PA has a zero entry in the second row and first column, where matrix A is given like that. This is 3 by 3 matrix. So how to solve it? In this particular case, we do not know the angle theta, and what we are going to do is we are going to find this angle. Find theta that satisfies our condition. Well, first we pick rotation matrix. Then we find product PA. But in this case, we do not know theta. Therefore, our resulting matrix will have general form, where theta is unknown. Now we need to use our condition. What we need? We need zero entry in the second row and first column. Second row here and first column here, which means that this entry should be 0. And this is exactly our condition, which allows us to find theta. And if we solve this trigonometric equation, we will get theta equals to 1 over 3. As a consequence, we of course can find immediately cosine and sine of our angle. Now we can compute the product PA and check if we achieved our result. And if you plug numbers instead of general form cosine and sine theta, this is your matrix P, this is your matrix A, and your resulting matrix has 0 entry, exactly what we wanted. This matrix is not symmetric and not tridiagonal, but this is the key point and this is the key step what we are going to use in order to understand QR method. Now let's go back to our QR method. When we represent our matrix A1 as a product of matrix Q1 and R1, we use product of n-1 rotation matrices to construct upper triangular matrix R1. And we start from defining rotation matrix P2, then P3, and so on, Pn-1 and Pn. At every step we should pick different rotation matrix, and as a consequence we compute different angle theta. So we start here and we pick matrix P2. This is our first rotation matrix. Let me write it down. First rotation matrix. Well, as I showed in the example, we can compute easily theta. Since we know the condition, we want particular entry be 0, and we follow here this procedure. and in this particular case, at first step, we want entry 2, 1 be 0. It means second row and first column of the product P2A1 should be 0. Or in other words, I can say that this matrix A2, 1 has 0 entry in the position 2, 1. So, at the same time, if we look at the other entries of matrix A2, 1, it does not necessarily has 0 entries in positions 1, 3, 1, and so on. But, for example, if we look at this matrix, what I wrote here in more general form, we can say that entries 1, 4, 1n should be 0. Entry 1, 3 might not be 0. If we continue construct matrices, we can write down the general formula AK1 equals to the product of the rotation matrix PK multiplied by matrix AK minus 1 from previous step, 1, and PK is also a rotation matrix. So we want to get zeros here, and we can see that at this point up to K we consider AK, and up to K we have 0 entries here, and this matrix has non-zero entries only on the main diagonal, and entries below K position, K plus 1 to n, since it's not affected yet, and we have certain non-zero entries on the positions 1, 2, 1, 3. The rest should be 0. Means we have 3 diagonal form here. So as I mentioned, that in general matrix PK is chosen such that KK minus 1 entry in matrix AK1 is 0, and I showed you how matrix AK1 looks like on previous slide. Now we should define matrix PK plus 1. This is our rotation matrix at the step K plus 1. And here we have identity matrices. Here these are matrices with 0 entries. All entries of these matrices are 0. And these coefficients actually represent our rotation. Here we introduce notation. Ck plus 1 equals to cosine of our angle theta at step K plus 1, and Sk plus 1 equals to sine theta at step K plus 1. And our goal is to ensure that this expression equals to 0. It means that we have 0 entry at a certain position. In this case, K plus 1, K entry in matrix AK plus 1, 1 is 0. And this equation, let's say equation star, ensures that we will have this condition. So since we deal with cosine and sine with trigonometric functions, we can use basic trigonometric rules, and we can easily find theta. And as just to remind you that theta we define at every step. For every rotation matrix we define new theta. So matrix A k plus 1, 1 has the following form. On the main diagonal we have non-zero entries. Also we have non-zero entries on subdiagonal, which is above the main diagonal, and one more subdiagonal. Then we obtain 0 here, and since we consider K plus 1 matrix, here we still have non-zero entries. So, but here all entries are 0. If we proceed the construction of sequence of rotation matrix, we will get the upper triangular matrix. R1. This is our notation. R1 or matrix AN1. What we have here, this is a matrix that has 0 entries below the main diagonal, and then we have non-zero entries here, main diagonal and 2 sub-diagonals above the main diagonal only. The rest entries are 0. The next part of QR factorization is the matrix Q1, which is a product of our transposed rotation matrices from P2 to Pn. Because of orthogonality, as we remember, the rotation matrix is orthogonal, and it's because of definition, and definition implies that P transposed, it's identity matrix. So then we should write this product as follows, and we just plug this expression with the product of our rotation matrices transposed and multiplied on R1. This is our upper triangular matrix, what we just computed on previous slide, and we can show that this product is equal to A1, and it's easily to see since we have this property. Matrices are orthogonal, and as a consequence these products will be identity matrices. If we proceed, like, we will have this product at every step. We move from the center and we will get A1 in the end. So the matrix Q1 is orthogonal. Because of that, we can write down this expression and this product, matrix Q1 transposed multiplied on matrix Q1, and if we compute this product we will get identity matrix. This is the same argument because our rotation matrix is orthogonal. By orthogonality property we can compute this product very easily and get identity matrix in the end. And by using properties of orthogonal matrices, we will see that Q1 is orthogonal. In addition, Q1 is an upper Hessenberg matrix. What means upper Hessenberg matrix? Let me remind you the definition of the upper Hessenberg matrix. A square matrix n by n is said to be an upper Hessenberg form if matrix A with elements aij has elements aij equals to 0 for any I greater than j plus 1, for any I and j from 1 to n. So, as a consequence, matrix A2, which is product of R1 and Q1, is also an upper Hessenberg matrix, because multiplying Q1 on the left by the upper triangular matrix R1 does not affect the entries in the low triangle. So, we also know that it is symmetric as well, and A2 matrix is three-diagonal matrix. The entries of the diagonal of matrix A2 will generally be smaller in magnitude than the corresponding entries of matrix A1, and matrix A2 will be closer to being a diagonal matrix than matrix A1. If we repeat this process and compute matrix A3, A4, and so on, we can get almost diagonal matrix. And entries, we can get very small entries of the main diagonal. And at a certain point, we can consider them as zeros. So this is our goal. We achieved it. We were able to obtain diagonal matrix, and as a consequence, we can find all eigenvalues of our original matrix A.